Today we're going to learn about antidifferentiation and indefinite integrals. Go ahead and begin by differentiating the following. Remember that the derivative of any constant is just 0. So what should you get when you antidifferentiate? F prime of x equals 3x squared. How would you find f of x? To find the antiderivative, we do something called an integral. This symbol is the integral. The function after the integral is called the integrand, and dx means we are integrating with respect to the variable x. So we can see that 3x squared comes from deriving x cubed. But what we don't know is if there was some sort of a vertical shift, some sort of a constant that when derived became 0. So anytime we integrate or find the antiderivative, we have to put plus c in order to account for that possible constant or that possible vertical shift. Just like our basic derivative rules, we can use those for integration. The integral of x to the power of n would be x to the n plus 1 over n plus 1, right? The opposite of the power rule for derivatives. If k is a constant, then our antiderivative is kx plus c. You can take a scalar multiple out of an integral just like with a limit. Constants may be factored out of the integral expression, but never factor out a variable. You can never take a variable out of the integrand. If your integral is the sum of two functions, then you can integrate that sum separately. Let's begin by integrating or evaluating the integral of x cubed with respect to x. This is written as a power, so we can use the power rule for integration, and that means we're going to add 1 to the power, and that power is our denominator, and we need to put plus c in case there was a constant. That's going to just reduce to be 1 over 4 x to the 4th plus c, and that's our integral. If you integrate a constant with respect to x, the result is just 2x plus c, our constant. Here we're integrating a sum of two functions, so you can separate this to be the integral of t to the 4th with respect to t plus the integral of 2 with respect to t, and integrate separately from there. The integral of t to the 4 would be t to the 4 plus 1 over 4 plus 1 plus 2t, since we're integrating with respect to t, and then plus c. You don't need to put plus c, which would be 2c, because 2 times a constant is still a constant. Here we can integrate each of these separately with respect to y. We have some scalar multiples that we can take out of the integrand. And now we can use the power rule for integration to find the result. Y to the 3 over 3, y to the 2 over 2, plus 1y plus c. For these two, we can use the power rule for integration as long as we rewrite these as powers. We can also separate this into two integrals. If you want, we could take out this 3, this scalar multiple. And now we can use the power rule for integration. Simplify. Try writing this function as a sum or difference of powers, so you can use the power rule for integration. Note, put plus c when you integrate, but never when you differentiate. Sometimes an initial condition is given which makes it possible to solve for c. If f prime of x is x to the negative 3 and f of 1 is 3 halves, find f of x, the antiderivative. F of x is the integral of f prime of x with respect to x. Our integrand is f prime of x, which is x to the negative 3. Go ahead and use the power rule for integration. This right here is our indefinite integral, but we can actually solve for c, our constant, by plugging in the point 1, 3 halves. So our constant is 2. That makes f of x negative 1 over 2x squared plus 2. To evaluate the derivative of an integral, if you were asked to evaluate the square root of 3 squared, you would know that the square root and the square undo one another, and you'd be left with the radicand 3. So when you derive an integral, you are simply going to be left with the integrand. What about plus c? Well, when you integrate, you would put plus c, but then after integrating, when you derive, that plus c would derive to 0. That's why the result is simply the integrand when you derive an integral.